Hey, sorry, this video is not finished. I just felt like at a certain point I needed to just upload it, and so if it seems a little unpolished, that's why. Enjoy.
How do you make a talking calculator? Well, you start with the buttons. When you first start learning microcontrollers, you probably use a button like this. The button is connected to a GPIO pin on one side and ground on the other side. The pin is what we call pulled up, which just means that it is outputting power and it will detect when it is pulled down to ground, like when you press a button. This works great when you have about 5 or so buttons, but we are building a calculator. Calculators have a lot of buttons, and ours is going to have 48. If we need to wire up each button to its own GPIO pin, that would just be a mess and take up a ton of pins. The highest pin count on a microcontroller that I am aware of is on the Teensy 4.1, and even that would be taking up almost all of the I/O. Also, the complexity of designing a circuit and corresponding code would be too much to deal with. So, what can we do? We use a button matrix. One side of each button is hooked up to a row, and the other side is hooked up to a column, creating a 2D grid. The rows and columns each are hooked up to a GPIO pin on our microcontroller of choice. It's similar in concept to the standard button, but with a few more steps. In the loop, we will pull the first column pin high and keep the rest of them low. Then, we subsequently check each of the row pins to see if there's a voltage on it. If there isn't, then we pull the next column high and loop through the rows again. We repeat this until we run out of columns or we find what's being pulled high due to the circuit being completed. If we find one, we are able to get the row and column of the button pressed and map it to a function. But shouldn't there be a diode on each button? Yes! I won't go into too much detail, but without diodes, if we push multiple buttons, we can have ghosting and other weird artifacts. If you want to learn more, I'll link some stuff in the description. I decided to take this trade-off and leave them off. This is a hand-assembled PCB, and 48 buttons is already a lot. I am still very new to PCB design, and the more simple I can make it, the much better. Also, this is a proof of concept and will improve with time. So, what microcontroller did we decide to use? Well, the Teensy 4.1. People who build their own keyboards use Teensies, and they are great for handling a lot of I/O. Since they can handle so much I/O, why don't we add some more? The best way to control volume is sliders and knobs. We don't really have room or even want a slider on the calculator, but a knob would be great. There are two types of knobs. The first kind is a potentiometer. A potentiometer is essentially a resistor that you can control by spinning it. If you turn it to the left, it will have the least resistance, and if you turn it to the right, it will have the most resistance. This doesn't fit our needs, as we want to be able to spin the knob forever, and resistors have a set range to travel to. A rotary encoder is a knob that can spin forever and has steps. I won't dive into the specifics about how this works, but I have linked the library we are using, which explains it very well. The pins on the encoder need to be pulled up. Instead of doing this on the microcontroller internally, like we did with the buttons, we will be doing this externally by connecting the 3.3 volt power through a resistor and the GPIO pin to the Teensy. We will do this for both encoder pins and the button pin. We will connect the other two pins to ground. When we spin this dial, the state will change and will send a signal to the microcontroller, causing an interrupt. An interrupt just tells the Teensy to pause whatever it's doing and deal with this new input real quick. We can interpret these in software. Since this is a talking calculator, we need to make it talk. The easiest solution is a library called Talkie, which can play pre-recorded voice samples. This would be great, but we want to make this something anyone can write code for, and if we have a limited vocabulary, that would interfere. This leaves us with the solution of speech synthesis. Speech synthesis is very computationally heavy and cannot be done on the Teensy. Luckily, there are other types of microcontrollers. An ESP32 is a family of microcontrollers made by Expressive. They have more RAM and computational power compared to most other microcontrollers, making them the ideal candidate for a TTS companion. Thanks to the amazing work done by Phil Shetman, we can run the flight engine on this controller. Phil has done literal magic to make this work. and it barely fits within the tiny flash and RAM limits of an ESP. But why don't you just use a Raspberry Pi Zero? It has so much more power. Raspberry Pis are awesome, and I love them, but they are not really ideal for this use case. They consume a lot more power and don't handle I/O as well. Also, Raspberry Pis run Linux, meaning that it takes time to boot up and more can go wrong with that added complexity. A microcontroller is just a better solution for an embedded device like this. There are a lot of options to buy an ESP, as an ESP is just a processor, and many companies put it onto their own dev boards. We went with the Seeed Studio Xiao ESP32S3. It is really small and can run flight unlike the C3. It has just enough GPIO pins for what we need. Now that we can generate some speech, we need some way to output it. A digital to analog converter, or DAC, is equipment that can take in a digital representation of a signal and make it into an analog output. Every modern device with sound output has a DAC, and we can hook one up here. But how do we tell the DAC what to play? We do that using an I2S interface. An I2S interface has 3 connections that I don't know anything about. The ESP can handle this all natively, so I don't need to worry about it. When the ESP generates voice data, it will send it over the I2S interface, and the DAC will convert it for audio for us to hear. Now, how do we switch between the speakers and the headphones? When you plug a device into your phone or your computer, the device senses that you plugged something in. This means that we need software to be monitoring and controlling a pin that tells when things are plugged in. Instead of dealing with all of that software complexity, we can trade that off for electrical and mechanical complexity. Wait, mechanical? Inside of an aux jack, there are 2 levers that act as springs. When we plug in a cable, it will push those levers out of the way and it will rest on the plug, making a connection. Now, instead of just having 2 levers floating there when the jack isn't plugged in, we can add 2 metal bars for them to rest on. When the cable is plugged in, the levers lift and act exactly the same. But when you unplug it, you will make a connection with those bars we added, which we can hook our speakers up to. This mechanical audio switching mechanism is called a closed-loop audio jack and is what we have here with our speakers. So we have a functioning circuit that allows us to generate speech and output it. But now we need to connect the I/O and math functions on the Teensy to the speech on the ESP. All we need is 2 wires and we can communicate over serial. Serial is an incredibly simple interface, so it's very reliable. It's also the same interface that is used on double talk chips, which, as I'm told, a lot of blind tinkers are familiar with. We hope to implement compatibility for that in the future, but for now we just send the numbers and words that we want it to say, and we use a special shebang followed by a V for volume adjustments, and that's it. Last thing we need to figure out is power. We don't want this calculator to be powered off of a USB-C and micro B cable at the same time, so we need to add a battery and make sure both components are powered off of it. Let's deal with that part first. This is a mini boost from Adafruit. It can take in 2 to 5 volts and output a constant 5 volts. We'll hook this up to each 5-volt input. In between, we are going to put a Schottky diode. A diode only prevents power from going one way, and so by putting a diode here, we prevent damage to the rest of the components in the board. Our power source is going to be 3 AA's powered through a barrel jack. This will output 4.5-ish volts max, and they will stay above 2 volts until they are low. But couldn't you just use a rechargeable battery? Yes, probably pretty easily too. The biggest reason why we didn't is because power circuitry scares me. Contrary to what it looks like, I don't like spending money, especially when I broke it by doing something stupid with power. So we just didn't deal with that. Also, it's version 1, so we're staying simple and it'll get better. And we built it. Let's recap how this all works together. Either I turn the rotary knob and the Teensy pulls it, or I push a button and the Teensy scans row by row, column by column to find where on a 2D grid I pushed a button. We'll then do some code magic and tell the ESP what it wants it to say over serial. The ESP does even more magic and makes a digital signal of the speech that we want to play and sends it over the I2S connection to the DAC. The DAC will take that signal, turn it into an analog signal, and send it to our closed loop jack. If our headphones are plugged in, the jack will output to those. But if there isn't any, it will route to the audio. All of this is powered over 5 volts that is boosted up from whatever the AAA batteries are outputting.
1 plus 2 3.00000005 times 3 15.0000000